Hi everybody, welcome back to our lecture Audio Coding, today about parametric coding of high quality audio. My name is Gerald Schuller. So what's the difference between waveform versus parametric coding? So in a waveform coder we have, as we saw, a filter bank approach. This mainly exploits limitations of the human auditory system, and it's a mature technology. In parametric coding, we have a source model approach, and this exploits both the source model as well as limitations of the human auditory system. And most audio coders use a combination of both. So we already saw a few parametric coding tools, for instance, spectral noise substitution, where we generate noise in the decoder. Today we talk more about spectral band replication. We already saw its use. Then we talk about the full synthesis. And actually last time we already talked about spatial audio coding. So now for spectral band application. This is in the MPEG-4 bandwidth extension. The background here is that audio coding at very low bit rates leads to artifacts, and to avoid excessive artifacts, the bandwidth is usually sacrificed at low bit rates, say below 14 kilobits per second per channel. And that means the signal sounds unattractive or muffled. The concept here is to regenerate the high frequency signal content at the decoder end from the low frequency part, together with some helper information, and this is parametric information that is sent from the encoder to the decoder. Yeah, so this is the idea of spectral band replication. So we regenerate the high frequency part of our signal spectrum by means of transposition of the transmitted spectrum. This ensures preservation of the harmonic structure. So transposition means we take the spectrum of the lower frequencies and basically transpose it to the high frequencies as a template, and then we shape this template such that it fits. And in this way we also keep the harmonic structure. By shifting the spectrum from the low frequencies to the high frequencies, we have the harmonic structure inherently in it. So subsequently we shape the signal towards the original time spectral envelope by an adaptive filter. So this is what I mean by shaping it. We have this template and then we shaping it with an adaptive filter. Basically we change the envelope of the spectrum such that this envelope is more similar to the original. So it resembles the original more closer with the help of this shaping and with the help of additional information coming from the encoder. And then there are some provisions for handling special situations. So for compatibility, we have the spectral band replication bitstream elements, which is about 2 kilobits per second per channel, can be stored in the AAC bitstream in a compatible way. So that's convenient because that means that even if you don't use it, you can still encode the low frequency audio. So the standard AAC decoders decode the AAC part only, which means without the spectral band replication. Yeah, this is MPEG-4 audio extension 1, and the spectral band replication is used, for instance, in high efficiency AAC, also called AAC Plus and MP3 Pro. Yeah, so here you can see the spectral band replication scheme, the principle. So here we have the AAC, the high efficiency AAC bitstream. We get to this bitstream parser. So this is in the decoder part. And here we have the low frequency audio encoded as usual using the AAC decoder together with the analysis filter bank, and this gives us the low frequency audio. Then at the same time, embedded in the bitstream, we have the spectral band replication information, which is decoded by this SBR parameter decoder. This also goes into the same type of filter bank, but now it also has this information for the high frequency generator, right? So this is where the transposition happens. So it takes the low frequency audio, which is reconstructed on the left-hand side, transposes it to the high frequencies, and inserts it into the subbands of this filter bank for the high frequency subbands. And then here the SBR parameter decoder is then using the information coming from the encoder to accordingly shape the subbands at the high frequencies. Yeah, and after shaping, this is simply added to the complete spectrum of our audio signal and together synthesized in this synthesis filter bank. Yeah. So usually with the SBR we have this extra filter bank here. So this is how it looks like. We have our original spectrum. So here we can see at the low frequencies we have the highest energy. Then this black line here is the masking threshold, and the gray line shows the spectrum of the signal, and this dark gray bar here represents the quantization noise of 16-bit PCM. So that's the quantization noise of the original 16-bit encoded audio. Then after in the encoding process we shape the noise. So, we have more noise now because we have lower bitrate. The lower the bitrate, the more noise we have, and it's important that the noise is not going above the masking threshold such that it stays inaudible, which we have here, and here we can see still the original signal. So this is basically ideally the signal coming out of the decoder. We have the noise stays inaudible, a lot more noise than in the original, but still inaudible, and in this way it should sound fine. Yeah, so when we go down in bitrate, we have even more quantization noise, but now we have no choice. The quantization noise is going above the threshold, right? So we have a violation of the masking threshold, and that means because of the lower bitrate, now we have audible artifacts. And these are noisy artifacts, and these are usually kind of ugly artifacts. So that's why instead, what those coders usually do is they just cut off the frequencies at some point, such that we have fewer information to encode, and such that we can keep the quantization noise below the masking threshold. So now altogether we have less to encode. That means we have less quantization noise, and we can still hide the quantization noise below the masking threshold. But of course this is audible, right? But instead of having those noisy artifacts, we now have this muffled sound, which is also not nice, but it sounds more natural than the noisy artifacts. And that's why people chose this compromise. Yeah, so with the bandwidth extension, what it's done is we take the information from the lower frequencies here and just repeat it at the higher frequencies. And of course it's not the same as the original, but it has the same tendencies. So it still goes down here just at a higher level. So what we need to do now is to make it more suitable to the high frequencies, which in this case means mostly attenuate those high frequencies. Yeah, and that's happening here in the next slide. Here we see that we attenuated and shaped it somewhat such that it looks more similar to the original. And since the ear is not as sensitive for high frequencies as for low frequencies, the differences that we generate here are not as audible as if we would do it here in the low frequencies. And it's actually sounding, even though it's not sounding exactly the same, it sounds more pleasant than having just the low frequencies. Yeah, so here are the properties of parametric coding. So this uses now full synthesis. So what we just had was just regenerating high frequencies, right? So these high frequencies are basically artificially generated from the low frequencies. Now we can do the next step, going to full synthesis. So here we have the coding of low bitrate per object. Object means now an audio object like a voice or a music instrument. And that also means the more audio objects we have, the higher the bitrate becomes. So this already shows you that this full synthesis, this full parametric coding, works best if we have simple objects like an instrument or a voice. Yeah, so we also need to include perceptual properties like the separation of temporal and spectral events, separation of sinusoids and noise. Right, these are different audio objects, and also the ear is treating them differently. And it allows manipulations. So if you have parametric representation of sounds, we can change those parameters, right? For instance, the pitch. If we have frequencies of sinusoids, we can change the pitch, and also the time duration, time scaling, or other processing. So having a full parametric representation allows us modifications, manipulations more easily. Yeah, so in the filter bank approach, the compression ratio depends on the number of subbands. So for stationary signals, that means the more subbands we have, the more compression we get, right? So this is the compression gain, and the compression gain for stationary signals increases with the number of subbands. Yeah, but here in parametric coding, we have a different approach. The goal here is to have a very low bit rate, and the approach here would be a high number of subbands to obtain the high frequency resolution, right? So this would be the equivalent. And this assumes that the signals are stationary, right? Otherwise, the narrow band assumption is not true. So the next step would be to save complexity. We estimate the frequencies of sinusoids in the signal directly instead of using the filter bank. The assumption here is that the signal can be described as a finite number of sinusoids. So instead of having the audio signal fed through the filter bank with a high number of subbands, we now try to estimate the sinusoids directly in the signal. So examples for partly stationary signals with finite number of sinusoids would be flutes or string instruments or parts of speech. Right? Here you have just one audio object, and this has a relatively simply source model, like a limited number of sinusoids. So this is very stationary. Like when you have a flute, you have a stationary sound. It doesn't change too much. Same for string instruments, and if you have tonal speech, right, like vowels R and O. Yeah, and for the encoding, we estimate the frequency of the sinusoid and transmit frequency differences over time to the decoder. So if the frequency changes somewhat, we transmit this difference to the decoder. Same for the amplitude of the sinusoid. We transmit amplitude differences over time in dB. And since we have frequency changes, we also need to take care of the phase. We need to make sure that the phase transitions are smoothed in order to avoid artifacts. Yeah, it is difficult to find perceptual important sinusoids and estimate their precise frequency and amplitude. So if you have a mix of sinusoids, to begin with, you don't really know which are audible and which are not, or which are important and which are less. So the goal here is to find the right sinusoids and their precise frequency. And we do that by ordering of the sinusoids with their perceptual importance. And we use the masking threshold for it. So here's the masking threshold, and then we can see how far a sinusoid is above the masking threshold. So here, this first sinusoid is quite high above this masking threshold of the entire signal. So this is the most important. And then here, those in the upper end, I can actually omit because they are below the masking threshold. And these are then less important because they only have a smaller distance to the masking threshold. Yeah, and then for the estimation of the frequencies, we look at a subband signal and follow the phase and compute the frequency from the phase. So the assumption here is that only one sinusoid is in the subband. So we use, for instance, the discrete Fourier transform to it. We apply the DFT to a block of our audio signal. We need to have enough DFT subbands such that only one sinusoid is in each subband. And that means the DFT resolution must be fitting for the audio signal to encode. Yeah, and also that means the spacing of the sinusoids in the signal must be finite. So we cannot have a noise-like signal, right? There we would have infinitely many sinusoids. So the higher accuracy of frequency estimation in effect provides us with a virtual filter bank with correspondingly high number of subbands and hence high compression ratios, right? So basically this estimation gives us a resolution of a correspondingly high resolution filter bank. Yeah, and this approach to assume or compute frequency from phase gives us quite an accurate frequency estimation. Yeah, this shows how it works. We have our signal. So this signal consists, for instance, of our flute signal coming in. Then we apply our sinusoid estimation. So inside we have our DFT and then the estimation of the sinusoids which are present in the signal. And this estimates then the frequency and the amplitude. And this information then goes to the decoder. So this arrow shows that it is side information parameters to the decoder. So then in the encoder, those found sinusoids are then regenerated and subtracted from the signal until no sinusoid is left. And all what's left after subtracting all the sinusoids is just the noise which we cannot model with our sinusoids. So this is then the second component of our signal. So also in the flute, we have noise-like components from the wind noise. And here we do the noise estimation. So basically here we take the noise and estimate the spectral shape of this noise, right? This gives its particular characteristic. We need to have the spectral shape and also the amplitude. And for the shape we use line spectral coefficients. So basically we fit an FIR filter, the frequency response of an FIR filter to the frequency shape of the noise. So then we transmit those LPC coefficients together with the amplitude to the decoder as additional parameters. Right. And yeah, finally, we also need a temporal envelope. So our flute has a start, a rise, and then also decay, a fall. So somehow we need to represent this temporal envelope of this flute sound as parameters to the decoder. Yeah, and this is then the decoder. Here we receive the bit stream. Here we have the demultiplexer. Then we have the noise, the sinusoids, and the transients here, the temporal shape. This should be, I guess, the decoder here, Huffman decoding. Here we have the transient synthesizer, so the temporal shape, sinusoidal synthesizer, so this produces the sinusoids, and this produces the noise. And then all together are added up to the complete audio signal. So out comes the reconstructed flute. Right. Yeah, so basically the same thing again here. We have the demultiplexer, dequantizer here, And here we have the harmonic components, regenerated sinusoidal components, and noise components. Yeah, so here additionally we also have harmonic components. This is basically a more efficient representation of sinusoids. If we have a harmonic structure like in a flute, then we don't need to represent the frequency of each sinusoid separately, but if we know they are in the harmonic structure, then we can reduce the site information in this way. Yeah, so here we see examples. So here's something like a speech signal, and it has an envelope, which you can see here in the dashed line. And here you have something like an attack here, which is more like a step. So here in our model we have sinusoids, then we have noise, which is a pseudo noise generator and envelope model. So this is basically where the LPC comes in handy. Basically in the decoder we have this pseudo noise generator, which generates white noise, which means it has the same amplitude for all frequencies. And then we just send it to this FIR filter with linear predictive coefficients. And this FIR filter has a frequency response like the shape of the noise that we want to generate. So we just need to send this white noise to the FIR filter with those LPC coefficients, and we have our desired noise with a desired noise characteristic. Actually, we use a warped LPC envelope model, so this is actually more suitable to the ear because this gives us more resolution at low frequencies. Yeah, transients are important to achieve high quality. So in the standard there are elaborate transient models, for instance the Meixner transients, which you can see here. So this dashed line here is an example for it. And there are also step transients. So this would be an example. So this is just a simple step. And these defines envelope shapes. Here's the reference for it, Progress on Parametric Coding for High Quality Audio from 2008. Yeah, the signal under the transient envelope function is represented by sinusoids. Yeah, so more on high quality parametric audio coding. So we already saw that we have joint stereo parametric coding. So this is basically an extension to intensity stereo approach. But it has additionally interaural time differences and interchannel coherence. And it has a scalable stereo syntax. So we have a base layer and an extension layer. And we have a high parameter update rate, higher than harmonics and individual lines and noise, necessary to achieve high signal quality for all signal types. And we have a dynamically switchable update rate. So here you can see a typical bitrate, an example. Here we have sound files from the MPEG so-called SQUAM CD, right? 12 sound files. It's usually individual audio sources or audio objects at mono 44.1 kilohertz, and the bitrate is controlled to maximum of 24 kilobits per second. And here you can see the bitrate distribution. So the header gets 304 bits per second, so somewhat low. Then the transients is just 197 bits per second, quite low. Then we have the sinusoids, the birth, which means the beginnings, 3692 bits per second. And we saw when they continue in the next block, we just have the differences, so they are more efficiently encoded. But since we have many sinusoids continuing, this is actually the bulk of the bits. So we have 13,206 bits per second for the continuing sinusoids. Then we have the noise with our LPC model with 1,701 bits per second. So ARMA actually means autoregressive moving average. So here you have an FIR and an IIR part in it. but it doesn't really matter. The principle is the same. You have a linear filter which shapes the noise. And then you have the noise gain, which needs an additional 2147 bits per second. So that's the temporal shape of the noise. And altogether add up to 21,247 bits per second. So this is actually quite low. So this is quite nice. Much lower than, say, what we usually expect from perceptual audio coding, like 64 kilobits per second. But keep in mind that this is just for one audio object. So this works well for one audio object. You can also enter more than one audio object and it will do something, but it won't sound as good anymore. Yeah, so this is the Philips high quality parametric audio coder. So here's the encoder. We input a stereo signal, left and right. Here we have the parametric stereo extraction with the parameters into the site information here. And then we have the actual audio signal here using a parametric coder for the audio signal. This is doing the extraction of the sinusoids and the noise. Here the quantization and coding and transmission. And then here we have the same for the stereo parameters. Here we have left and right. Right. So here this is basically this block. Here we have a filter bank, a non-uniform filter bank, which mimics more closely what the ear is doing. And for each of those subbands, we then extract the interaural intensity differences. This is actually ILD, the level differences. Then we have the interaural time differences and the interchannel cross correlation here as site information for the decoder. Yeah, and this leads us to the full synthesis conclusion. The advantages here: we have the possibility to change the pitch, for instance, of a musical instruments or voice. Possibility to change the playback speed. You can just use the same parameters and play them back quicker or slower, right? Without changing the pitch. So that's convenient. And this gives us additional functionality. And recent development also gave us high quality stereo at about 24 to 32 kilobits per second. So that's actually quite good. And this doesn't necessarily need to use parametric coding. This can also be reached with AAC coder, for instance. Examples are the harmonics, individual lines and noise coder from the University of Hanover, the Philips parametric coder. So both are basically mix of both are now a part of MPEG 4 audio extension 2. Yeah, and here are references for further reading. Here from Mike Goodwin, Adaptive Signal Models, Theory, Algorithms and Audio Applications. Pornhage, Meine Edler, Speeding Up HILN, MPEG 4 Parametric Audio Encoding with Reduced Complexity. Then here MPEG 4 HILN and Parametric Coding of High Quality Audio. Okay, so that should be it. Thank you for your attention and yeah, happy studying. Bye bye.